My name is Yusuf Şamil. Me and my friends are representing TCP Congestion Control, focusing on two fundamental algorithms, TCP Tahoe and TCP Reno. Their goal is to maximize data flow without overwhelming the routers, keeping internet traffic moving smoothly across the globe. Now, let's look at some core mechanics. The most important concept here is the congestion window, or C window. Simply put, this is the maximum number of unacknowledged packets a sender is allowed to have in the network at any given time. It acts as the speed limit for our connection. Connections start in the slow start phase with a C window of just one maximum segment size. For every acknowledgement we receive, the window doubles, which means growing exponentially fast. When this window hits SS trash limit, it switches to congestion avoidance phase. To be safe, the growing becomes linear, adding just one MSS per round. But what if a packet loss? The system detects this in two ways. A severe jam causes silence, triggering a timeout. A milder issue causes three duplicate acts, meaning some data is still reaching the destination. Now, let's see what we talk about on graphics. Both algorithms behave identically at the slow start phase. After reaching SS trash, they switch to linear growth. But at round 8, as you can see, a packet loss occurred. Before understanding the behavior of Reno and Tahoe, let's explain the X and Y axis. X-axis demonstrates the transmission round, which means the receiving act message to receiver from receiver. The Y-axis represents C window, congestion window. But it is crucial to note that if this packet loss was due to severe timeout, both Tao and Reno would act identically. They would aggressively drop their window all the way to the 1 and start the procedure again. However, the graph illustrates a milder three-duplicate act scenario. Let's look at the difference. Following the blue line, TCP Tahoe treats all errors equally. It panics, drops the C window all the way back to 1, and completely restarts the slow start process. This wastes a lot of time. Now, following the white line, TCP Reno acts much smarter. It understands that receiving duplicate acts means the network isn't completely dead. Instead of dropping to 1, it simply cuts the window exactly in half down to the 6 and immediately resumes linear growth in a phase called fast recovery. To show you exactly how Reno's smart recovery operates behind the scenes, I will now hand it over to my teammates for code demonstrations. Thank you for listening.
Hello, my name is Halit. I will be walking you through the core behaviors of TCP Reno and providing a brief comparison with TCP Tahoe. We will focus especially on how these two protocols handled congestion and packet loss. For our analysis, we are considering three main scenarios: missed case, timeout case, and the triple duplicate egg case. While we can adjust the specific parameters and variables our simulation, the fundamental logic remains consistent across these scenarios. Scenario 1: the timeout event. First, let's look at the timeout scenarios. In the event of the timeout, TCP Reno and TCP Tahoe behave identically. Both protocols assume severe congestion and take a conservative approach. The congestion window is immediately reduced to 1, as you can see. The slow start threshold is updated to half of the current congestion value, as you can see. In short, both protocols hit the reset button to clear the network congestion. Scenario 2. 3 duplicate X, the turning point. The real difference between these two protocols emerges when 3 duplicate X are received. This is where Reno shows its strength. TCP Reno, when Reno detects 3 duplicate X, it triggers a mechanism called fast recovery. Instead of dropping the window all the way to 1, it sets the SS trash to half of the current CWND, and then sets the new CWND to SS trash plus 3. The plus 3 accounts for the 3 packets that have already been received and acknowledged. This allows Reno to maintain its speed and recover much faster. TCP Tahoe, in the same scenario, Tahoe is far more conservative. It treats 3 duplicate X exactly like a timeout. It drops the CWND straight back to 1 and sets the SS trash to half of the previous window. To sum it up, while Reno attempts to maintain momentum through fast recovery, Tahoe is more cautious and restart the window from stretch after any sign of packet loss. Now my friend Berat will take over to explain the rest of our findings.
Thank you, Halit. My name is Hanfi Berat Sak. In this part, I will demonstrate the topology side of our project and show how message forwarding works in our 6-node network. On the screen, you can see our topology plan. We use 6 nodes. Each node has its own configuration and routing information. This visual helps us explain why each message follows a specific path in the network. First, we compile the project with make. Now, to start the node-based simulation, we open 6 terminals and run these commands one by one. This starts all 6 nodes in separate terminals. Each node reads its port number and routing table from its own configuration file. Now we begin the forwarding test. In the terminal of node A, we send a message to node D. As we can see, node A selects node B as the next hop. Then node B forwards the message to node D, and finally node D receives it. This path is consistent with our topology. From A to D, the selected route is A to B to D, which is the expected forwarding path. Next, in terminal of node F, we send a message to node E. Here, node F first forwards the message to node A, then node A forwards it to node B, and node B forwards it to node E. Again, this matches the topology and the routing tables shown on the screen. The path is F to A to B to E, which is the expected route for this destination. So, in this demonstration, we verified that our node-based topology mode works correctly, that each node reads its configuration properly, and that the forwarding behavior matches the planned network topology. In conclusion, we successfully implemented TCP Reno, which was the required algorithm for our group. We also compared it with TCP Tahoe and demonstrated the topology forwarding path. Our results show that Reno recovers faster than Tahoe in duplicate acknowledgement cases. while also satisfying the required forwarding behavior in the network topology.